everybody, Mr. Covey here, and in this video we're going to learn kind of our last big integration technique, which is called integration by parts. Okay, when I say an integration technique, I mean a method for taking an antiderivative. Okay, I know it's been a bit since we've done this because we've been doing some other stuff in the meantime with integrals, but I want you to go back and just think of like, what are some strategies we have talked about for finding antiderivatives? What are some of the integration strategies we've talked about? There's actually quite a bit. So this is on the second page of your note packet. I'm kind of going to fly through a few pages right through your note packet, so if you want to have that out, or just jot these down. We're just going to be doing some integrals and learning this new technique. Okay. So pause real quick, take a couple minutes to think about the different ways you know how to take antiderivatives, the different techniques you can use. Pause, give it a try. Okay, and I just want to make sure our brains are working right and we're remembering all the things we know. So the first thing that came to mind was like, oh yeah, remember when we did all that stuff with U substitution? Check, cool. Remember U substitution was invented to undo chain rule. It was a reverse chain rule, okay? You just know a bunch of antiderivatives. Okay, you know how to undo, or you know how to do the antiderivative of x squared, it's x cubed over 3. You know how to do the antiderivative of e to the x, it's e to the x. You know the antiderivative of cosine, sine, that stuff. Menon-denom. Remember that menon-denom is just a simplifying technique, right? So you know how to take the antiderivative of maybe something that looks like this. X squared plus 3x plus 7 all over x. You know how to take the antiderivative. You know how to integrate that by doing that menon-denom idea. Remember, that's when you take that one fraction, that one fraction, and that one fraction, and then integrate those individually. Okay. Remember, division. Remember, we talked about this. When you have a polynomial divided by a polynomial, you can use long division or, in some cases, synthetic division to rewrite it in a way that you can then do the integral. Both of these are rewriting techniques. Trig identities. I know we didn't focus on that, but with the polar area thing, we were integrating cosine squared by using a power reducing formula, a rearranged double angle formula. Okay. Integration by parts. This is the one we're going to talk about today. Okay, this is a big boy technique. Write that down. Big boy technique. They don't learn it in AB. They can't handle it. Okay. It's a little bit tricky, but it's not going to be too bad. Okay. I kind of always think about it in partnership with EU sub. Okay. Cool. We're also going to learn today real quick the shortcut version, which is called tabular integration by parts. It helps when you hit certain integration by parts problems. Okay. Partial fractions, we actually talked about this yesterday, right? About rewriting using partial fraction decomposition in order to make it look in a way that you can integrate, and then completing the square we'll talk about more in this chapter. And again, it's using some algebra to rewrite something. So we'll talk about that. Cool. So you guys know a bunch of integration techniques. Today we're going to learn these two extra ones. Okay. So what I would like you to remember is that U substitution comes from chain rule, not product rule. It came from chain rule. Okay. If you remember, we were integrating something that was like you know the whole du part when we put our cloud and we made sure we got the du part in there? That's because we were undoing chain rule. So we were taking our integral and we were thinking about it as having chain rule applied to it and undoing that chain rule. Today we're going to learn something called integration by parts. It's the same thing but for product rule. So it undoes product rule. Okay? Okay, let's do this. In order to get this integration formula, we have to first make sure we remember what product rule is going forward. Okay, so what's product rule? Well, if you have a product, U times V, and you want to do the derivative of it, you do the first times the derivative of the second plus the second times the derivative of the first. And I'm going to do some derivation here, just stick with me. Let's say I integrated both sides. Integration's an operation, I can integrate both sides. Okay. But if I want to integrate that product, I could integrate u, and I'm going to rewrite v prime as dv, the derivative of whatever v was. Okay. And I'm going to rewrite the u as a, or the u prime as a du, the derivative of whatever u was. Okay. You with me so far? Okay. The antiderivative of the derivative of u times v is just uv. And I'm left with this statement. And I know this looks confusing, but just stick with me and this will all make sense once you start seeing some problems. And I'm just going to rearrange this. Okay? So I'm going to essentially solve for this piece of it. Okay? So I'm going to get that the integral of u dv equals uv minus the integral of v du. Okay? This is my integration by parts formula. I know this looks confusing. I promise I'll explain. But what this does essentially is it says if you can get an integral that looks like this as your original problem, you can think about your integral as being a product where one of the things is u and the other thing is dv, then you can rewrite it like this. And the thing that's always weird to me is that when the way that you rewrite it, this formula for finding an antiderivative has an antiderivative, has an indefinite integral in it. So it doesn't like do the whole thing for you, but it lets you rewrite the problem in a way that's going to be easier to integrate. Okay? Okay. Last thing I'll say, and then we'll do a problem. Notice that there's a lot of different variables going on in this formula. There's u's, and there's v's, and then there's derivatives of whatever u is and derivatives of whatever v is. So it's kind of like u sub where you pick a u and then you find a du. But because you start over here, you actually pick to start is you pick whatever you want u to be, and you pick whatever you want dv to be. And then you figure out the other two. Well, if you pick u, how do you find du? It's the derivative of u. If you have the derivative of v and you want v, you got to do an antiderivative. Okay? So you pick those two purple ones, and then you calculate the two blue ones, and then you have all four pieces of the formula, essentially. Kind of like u sub. Okay, let's do a problem. Cool. Again, so this is the integration by parts formula. U dv minus, or the integral of u dv equals uv minus the integral of v du. Okay, I know it's confusing with the u's and the v's. You need to memorize that formula. Okay, check. Very important. Time to just do a problem. Okay, so here's how this is going to work. You're going to start out by knowing that, first of all, let's just talk about the integral. I'm trying to do the integral of a product, x times cosine of x. It's a product, okay? Remember that u sub stuff looks like a product too, but the difference here is that if I tried to do u sub, don't write this down. Like I'd make u the inside part, so I'd make it x, and then du would just be 1 dx, and then I'd make it cosine of u, but I'd still have the x chilling there, and now I have u's and x mixed, and I can't. Okay. So this isn't u sub. This is maybe an x squared into u sub. What is that? So I need to use this integration by parts. Okay. Please remember, last thing I'll say, and then we can actually do it. You can't just do the antiderivative of both parts. Please don't write this. Write this. Mrs. Lemke's going to freak out. It doesn't make, I'm going to freak out. That doesn't make any sense. You know that's not right. The antiderivative of this isn't this, because if you did the derivative of this, you'd have to do product rule, and you wouldn't get this. Okay, so that's totally not right. We need a more sophisticated technique, and we're going to use this integration by parts. Okay, so always set it up like this. You pick the blue ones. The blue ones are the things in your problem. I'm going to tell you that we're going to make this one U, and we're going to make this one D. Okay, don't ask me why. We'll talk about it later. Okay. So U is X, dV is cosine of X. We can really call it cosine of X dx if you want. And now we need to finish filling this out. Well, we have U. How do you find du? You do the derivative. What's the derivative of X? Just 1. You have dv, the derivative of v. How do you figure out v? You do the antiderivative of it. What's the antiderivative of cosine sine? Okay. I forgot to say the most important thing, and I know what you're thinking. You're like, for U sub, we put everything in a cloud. And I love the Cubby cloud. Or excuse me, I love the cloud. What do you do for integration by parts? You put it in a pillow. Okay, you make a nice little ornamental pillow. And so for integration by parts, you put all that information in the pillow. Okay? Cool. And now we're going to use our formula. I'll write it down here. But you do need to memorize it. Please make sure you can tell the difference between your V's and your U's. Okay. So we're integrating this, u dv, okay? And the way we're going to do that is by finding u times v minus the integral of v du. Okay? I can't emphasize enough, sorry, and this is, we're finding this antiderivative, this integral. You can't emphasize enough the weirdness of the fact that the formula for finding the antiderivative of this that we're using has an antiderivative in it. You're like, I wanted to find the antiderivative. Why do I still have an antiderivative? Well, what's nicer about this indefinite integral compared to what I started with? Well, it's actually an antiderivative you can do. Okay? So although the formula still has an integral in it, the idea is that what you're left to integrate is simpler than what you were originally integrating. Because I can't do the antiderivative of cosine of x times x. So I'm rewriting it using this formula, and the integral part I can actually integrate. Okay? So I get x times sine of x, and then I actually need to do that integral. What's the antiderivative of sine? Negative cosine, so then minus negative cosine, so plus cosine of x. Plus c. Okay? And that's the antiderivative. That's my answer. Cool. Check. Okay? Let's move on. Do another problem. Here's some memes. It's kind of weird to use and V's and DV's, and it does sound weird. Okay. I want to show you something cool, which is that we can integrate ln now. And you're like, wait, I thought I already could integrate ln. No, no, no. We knew how to do the derivative of the natural log, but we've never known how to do the integral of it. And we can do it with integration by parts. I'll show you. This is kind of a cool problem. Integration by parts works for products, but natural log of x isn't a product. But if I wanted to write it as a product, I guess I could think about it as like ln of x times 1. Okay, cool. So now it's a product, so now integration by parts might help me. I need to pick a u and a dv. I'm going to tell you right now I'm picking that as my u, and this is my dv. If you're like, how are you choosing that? I'll talk more about it in a minute here. Okay? So then u is ln of x. So then du is 1 over x dx. dv is just 1. Yeah. So then v is the antiderivative of 1. It's just x. To put an integration by parts pillow, very important, very important. I can use my formula. The integral of u dv equals u v minus the integral of v du. Again, the purpose of integration by parts, not the purpose, but a nice thing that happens, is that the integral that you're left with in the formula better be something you can actually integrate. Okay, what's the integral of 1? Well, it's just x. So my answer is ln of x times x minus x plus c. That's the antiderivative of ln of x. Integration by parts gives you complicated antiderivatives. Okay, like there's no way you're going to glance at ln of x and think that the antiderivative is ln of x times x minus c, or minus x. Okay, that's just kind of cool about the formula. It's a little bit more interesting. Okay, you can't like wing it. Uh-oh. Another meme. Okay. We're going to see something here that's not good. Okay. So we're going to do our integration by parts. Again, why we're doing this technique is we're trying to integrate a product. Okay. And U sub or any of my other techniques won't work. So we're going to use this integration by parts technique. I'm going to pick this is U dx is dv. Okay. I'm going to set up my pillow. I know U. I'm going to find du. I know dv. I'm going to find v. Antiderivative of e to the x is just e to the x. And I'm going to use my formula. The antiderivative of u dv is u v minus the integral of v du. That should be a dx, I bet. Take a look at where I'm at now. Okay, so I'm doing my antiderivative. I got x squared e to the x. And now I got to do the antiderivative of... Oh no. Oh no. What's happening here? Hope you got your brain turned on. You're thinking about this. What happened here? Well, I got this integration by parts formula that has an integral in it, and the integral that I had in it is supposed to be something that I know how to do the antiderivative of easy. But this isn't something I can do the antiderivative of because it's another product. Oh no! How do you do the antiderivative of that? Well, it's e to the x times 2x. A u sub won't work. Oh, I know what I could do. I could do integration by parts again. It's like integration by parts within integration by parts. Okay, because in the integration by parts formula, I got the integral part still was something I couldn't integrate myself. So I have to do integration by parts again. Okay, how do you do it again? Well, you pick another u and another v and or dv, and you find du and you find v. Make sure you keep all this straight though, because now we're kind of calling something u again, which is a little bit sloppy mathematically. But the way I get around it is I draw a smaller pillow. Right? Like if the original pillow was like a big throw pillow, or big, I'll have to ask my wife the names of it. This is much more like a small couch pillow, maybe like a foot across, real small pillow. I'm going to call u e to the, sorry, I'm going to call u dx, du is therefore 2. I'm going to call dv the other part, e to the x, so v is just e to the x. Notice that when I pick the u and the dv, it does have to incorporate the entire thing. So like if this is u, or sorry, if this is u, then this is dv. Yes. And now I'm going to use my formula again. within this other problem. It gets a little messy, so let's try and do it neatly. So I'm doing x squared e to the x minus integral of that. This integral, I'm going to use integration by parts with my throw. U v, I'm looking at the small pillow, minus the integral of v d. Okay. The nice thing that's happening here is that the integral that I do have now is something I can integrate. Okay, stick with me here. Here's where I'm at. X squared e to the x minus, in parentheses, 2x e to the x minus the integral of 2 e to the x dx. Okay, I am never going to leave my antiderivative with antiderivatives in it, with integrals in it. That doesn't make any sense. So I need to do this antiderivative. I need to keep going. What's the antiderivative of 2 e to the x? Well, luckily it's just 2 e to the x. So now I'm here. I'm almost done. And that's my answer. Okay, so I'll write it real quick. So the antiderivative of x squared e to the x is x squared e to the x minus 2x e to the x plus 2 e to the x plus c. This is what me and Mrs. Lemke have been saying when we say integration is messy. It's a lot messier than taking derivatives. Like, this is a crazy antiderivative, but this integration by parts technique gives us it. But what was different about this problem? We had to do integration by parts within integration by parts. Our integration by parts formula, the integral in it, still required integration by parts again. That's why we had to do it twice. Okay. If you are wondering about this u and dv part, like, how do you pick the u and dv? Mr. Carver just keeps deciding which one's u and which one's dv, and it works out. Well, there's a couple of ideas here. First, it's kind of like use of in the sense that you pick what works. Okay, so like, if you pick the wrong u and the wrong dv, then when you go to use your formula, you're not going to be able to do this. It's going to be messy. Okay. There is a little bit more of a formulaic process if you want, which is when you're picking the u is something that, remember when you're filling out your little pillow, it's a horrible pillow. Mrs. Covey would never let me put that pillow out. It looks ridiculous. When you pick the u, you have to do the derivative of it. Okay? So you got to pick u as something you can do the derivative of in order to fill out your pillow. Easy. We can do the derivative of almost anything. When we pick the dv for the other part, remember what we do is we find the integral of it. So when you're picking the dv part, you want it to be something that integrates easily, something that you can do the integral of, because otherwise you can't even fill out your pillow. Okay, does that make sense? So your choice for u should follow this order, because this is stuff that you can do the derivative of, but is difficult to integrate. I will say that again. This order is stuff that you should pick for u. So this tells you in what order you should pick u, based on the fact that these are types of functions starting at the top that you can do the derivative of easily, but they're difficult to integrate. So you don't want to pick these as dv if possible, because then you have to do the antiderivative of them, and that's messy. The acronym is LIPIT, and what it stands for is what type of functions you should pick for u in integration by parts. And it's saying you should pick logarithms first for your u if they show up, inverse trig functions if they show up next, polynomials, exponentials, and lastly, trig functions. So you should look at your integral, and when you're deciding, one part's u and one part's dv, I can't emphasize enough that the entire thing has to be taken up. So whatever is u, the other part's dv. You're going to pick the natural log for u, if there is one. If not, pick the arctan, the inverse trig, if there is one. If not, pick the polynomial. Okay, so if you go back here, we were using lipid here. I went down my lipid really quick. I'll show you. I was trying to pick the u, and I said, is there any natural logs? No. Is there any inverse trig? No. Is there a polynomial? Yeah, x squared. I'm picking that as u. I didn't pick the exponential because that's below. So I left, once I picked that my u was x squared, whatever is left becomes the dv. If you saw that last example and you were like, oh my gosh, I can't believe we had to do integration by parts twice in the same problem. What happens if we had to do it thrice? Or 17 times? Don't worry, there's a shortcut. Okay, so what I'm going to show you is a shortcut for integration by parts. And now we're on the page 9 in your note packet, if you want to jump there. And if you hit an integral like this, like antiderivative of that one we did was x squared e to the x. If it was like x to the 10th e to the x, oh my gosh. We'd have to do integration by parts with an integration by parts with an integration by parts with an integration. We don't want to do that. It's really annoying. And that is what you have to do, but there's a kind of shortcut to do it. And it's called tabular integration by parts. Okay. When this is going to happen is when you're trying to use integration by parts, so you're integrating a product, one part integrates repeatedly. Okay, what does integrates repeatedly mean? Think trig and exponentials. Right? Like, what's the antiderivative of e to the x? E to the x. What's the antiderivative of that? E to the x. What's the antiderivative of that? It integrates repeatedly. What's the antiderivative of sine of x? Negative cosine x. What's the antiderivative of cosine? Negative sine. What's the antiderivative of negative sine? Cosine. Like that. Okay. And the other part differentiates to 0 in several steps. What does differentiates to 0 mean? It means if you keep doing the derivative, you get 0. The derivative of x to the 10, x to the 10th is 10x to the 9th. 90x, or 10x to the 9th. 90x to the 8th. 720x to the 7th. You know what I mean? Eventually, though, it would go down to 0. Once you did the 10th or 11th derivative of this, you get to 0. Okay. Here's how this works. We just did this problem before, recall? This is the exact same problem, integral of x squared e to the x. I'm going to show how you do it with integration by parts. Okay. Initial setup is exactly the same. I'm integrating a product. I can't use u sub. I'm going to use integration by parts. I'm going to think about my limit to pick the u. So I'm going to end up picking x squared as u, meaning the remaining part has to be dv. I'm going to draw my pillow. If u is x squared, then du is 2x. And if dv is e to the x, the antiderivative of e to the x is just e to the x. Okay. You can start doing integration by parts and realize that you're going to have to do it more than once and then try this other technique. Or you can just recognize, like I would, that this is going to differentiate to 0 in multiple steps. This part. This is going to differentiate to 0 multiple steps, and this part integrates repeatedly, meaning this tabular integration should give us the same answer. Right, here's how it works. You're going to make a column for u. You're going to make a column for dv. And we call du x squared, and we call dv e to the x. And what we're going to do is down the u column and keep doing the derivative and differentiate. Down the dv column, what are we going to do? What do you do with dv? Integrate. We're going to integrate down that column. Okay. What's the derivative of x squared? 2x. What's the derivative of 2x? 2. What's the derivative of 2? 0. What's the antiderivative of e to the x? E to the x. What's the antiderivative of e to the x? E to the x. What's the antiderivative of e to the x? E to the x. Okay. In this third column, we're just going to list plus and minus signs. Okay. We're always going to start out with a plus, and we're just going to alternate. Plus, minus, plus, minus. This all needs to be lined up. The reason it's called tabular integration by parts is that you are making a table. That's what we're making, is a table. Okay. If you recall, the answer to this problem, jump back, was x squared e to the x minus 2x e to the x plus 2 e to the x. And you look at this table we just made, it like has all of those components in it. How do you get the answer? You do this. Start at the top left, you go diagonal. Your first term is going to be x squared e to the x. Okay. We're just going to straight up grab the answer from this table. It's cool. Okay, so my answer is x squared e to the x. That term is going to be positive. Okay. Next, I'm going to grab this one. My next term is 2x e to the x. That term is going to be negative. Okay? So my next term is 2x e to the x, but I'm going to subtract that last one. Or next one. I should keep going down here. Sorry, just put a plus. Because the last term I'm going to grab is 2 e to the x, and that one's going to be positive. 2 e to the x, that one's going to be positive. And then I'm not going to grab another term, because if I grabbed another term, it'd have 0 hooked onto it, and so it'd just be 0. Don't forget, I just found an antiderivative, so always put a plus c on at the end, and this is my answer. Same answer we got by doing integration by parts twice, but I didn't have to go through that process because instead I used this little table here. And you don't have to use tabular integration by parts, but imagine doing integration by parts within integration by parts within integration without this, and it kind of becomes a pain. Knowing the tabular thing is cool. I know it's been a long video. I want to try one more problem here. Okay. Stick with me. Because this differentiates to 0 and this integrates repeatedly, not only am I going to use integration by parts, I'm going to try and do this tabular one. I'm going to call this u because it is a polynomial, and when I got on my limit, I hit polynomial before I hit trig part. Okay, limit. That's trig parts at the end. So if that's u, this is dv. I'm going to set up my pillow. I'm going to put the pillow with a little bit of fringe. I don't want to offend anyone if you guys don't like fringe, but sometimes fringe is nice on a pillow. I'm just going to say. Tasteful. That's what Mrs. Covey says. It can be tasteful. Okay, so if u is x cubed, then du is 3x squared. dv is cosine, so then v is sine. Again, you're either going to start integrating using normal integration by parts and realize that you are going to have to do it repeatedly, or you're just going to know that you're going to have to do it repeatedly and you're going to jump right into this tabular integration. Oh, tabular, because we're going to make a table. Table is u, dv, and then the plus minus sign. Here was the u I picked, here was the dv I picked. I'm going to integrate down the u column. I'm going to integrate down the dv column. The antiderivative of cosine is sine, antiderivative of sine is negative cosine, antiderivative of negative cosine is negative sine, antiderivative of negative sine is cosine, and then I'm going to toss down some plus minus signs. Plus, minus, plus, minus, plus, minus. Please note that don't make the mistake of grabbing them like this. Like, that's not how it works, right? You have to grab them at an angle. So they go boom, 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 boom. Sorry, give me a second. Now I'm just going to line those terms up, and I'm done. Watch. My antiderivative of x cubed times cosine of x. The antiderivative of that is x cubed sine of x, which is positive. 3x squared times negative cosine, but with another negative sign, so it ends up being positive, plus 3x squared cosine x. 6x times negative sine x is negative 6x sine x. It's positive. 6 times cosine x is 6 cosine x, but it's negative, so I'm going to subtract it, minus 6 cosine x. It's an antiderivative, so I'm going to toss down a plus c, boom, we're done. Okay. We're obviously going to practice this technique. It's a tricky technique. Thank you for watching this really long video. I know there's a lot in it. Cool. All right. Thanks for watching, guys.